So thank you so much for the invitation. I want to share with you a few ideas and fuel for the mind. If you're interested in more technical work, please come to see us for the conference. But I enjoy things. We're here for quite a long time just talking about one thing. And
Ryad, can you hide that thing with the...
I can't. I don't know how to do that.
Yeah,
huh?
Hide that stuff at the top. No, the 3 dots. No, to the right.
Here.
Yeah. Click hide something. Yeah.
Hide, yeah. Wow. And so this idea is always about, I think the field is always asking question about events and frames are a different world, events are a different world, and people are frames, events. People shift between events and frames, but reality is, what I want to say in this talk, they're somehow very similar and very different, and one includes the other. We'll get there. So if I had to rephrase this talk, it would be something like this. Basically what I'll be talking about today is the importance of understanding structure and statistics, because basically this is what both information are providing you, and I'll get there. So we'll do it like a petit zero equations will go there. So since I joined computer vision in 1993, I've seen this community change 3 times directions, and so I wanted to understand the timeline of where we came from. Why are we all here? And obviously there are some important dates. 1958, this is the invention of perceptron, and then you had 59, the Hubble and Wiesel, and then the first picture, digitized picture, and then there was this birth of computer vision around the 60s with Larry Roberts, who started doing all the filtering. And then there was, of course, the summer of vision, where computer vision thought people would solve it at MIT for a summer project. Of course, it didn't happen. And then Larry Roberts could be seen as the father of computer vision, just because he did it, and then he ran away building internet, I think. And then the second father of the field could be seen as Rosenfeld. Everybody who dominated the field in the 80s and 90s somehow passed through that lab. It was a hub. And then, of course, the David Marr that dominated the field, this idea of, hey, I have an image, I'm going to extract something and something and something, and it's hierarchy, like the vertical hierarchy, which I think is now has to be changed into a horizontal, but it's a different story. And then the 90s, all of us here, some of us are from the 90s here, we all did geometry a lot. And then the thousands, it was all the quest of, now we solve geometry, how can we solve pattern recognition? So the 2000 was the SIFT, but with no machine learning yet. And when you look again, around the 2000, we have GPUs, and we start having, this invasion of AI. So you see the fields go and changes, and people change and people adapt. So reality is now, since 2000 with the GPU, the game is mainly a game of data collection and data training. So we academics, I'm not academic anymore, but are out of this game, right? So it's really a game of power. And so the question is, what's going to happen next, right? And so on the other hand, this is frames, events. Whereas, you see, things change. There is no truth. So, this is not my work. Really, it was presented at ICCV in 2019. Someone said, computer vision looking back to look forward. And she really realized that computer vision has been reinvented many times, and that the computer vision community resists novelty. So obviously you're all here because most of us did the great work to advertise and get you here, and so thank you so much. Now look at this thing. We dedicate in our community 2% of our time to think about the fundamental of what we do. Isn't that a problem? 2% of the papers accepted here think about what we should do next. This is really a problem. So we are a very good community of engineers, and I think sometimes it's nice to have something new that comes and shifts, because at the end it's engineering that prevails, right? So my question, for many reasons, around the end of the 90s, because most of us Here we're working on fancy cameras and going beyond geometry and single viewpoints. And it never really worked. And my opinion was because the images are something really bad. And so I asked myself a question. Why are we using images? Why are images the optimal structure of data? Is it true? So now we know probably not. And are the gray levels really what we need? Just a very simple question. And I think I got the answer for that. Because when you really look back, why we try images, I think the answer is, I said it many times, it's a momentum of history. It comes from painting. Everything we do here started here. This is the mother of all camera. It's called the camera obscura. It was fun to do, but suddenly it reaches us because people made money out of this. There was a money approach, and people start painting faster, and so it's a momentum of history. And when we talk about event acquisition, now people think DVS, and it's a very good solution. So I'm not reminding you all this, you know all this. It's basically changing from sampling on the time axis to another dimension with this amplitude, and you can do all the fancy things. So it's a good way. That's why we're gathered here to talk about this. Reality is, time is the most valuable thing in this framework, and I will show you why it is so important. And so, obviously, DVS, old days. I have the first 128 DVS soldered by Toby himself. Should keep it in the museum one day. And then we see this new type of sensors that are called hybrids. So the hybrids has a very funny story. Toby and I in 2007 wanted to write the European project, remember? And I told him, it's a problem that we don't have photo consistency. At some point I would be happy to have a gradient to know how much light is going. Not all the time, but sometimes. And brains do it. Brains have frames and they have events. So this was the starting of this design, and that Rafa did first. And don't get me wrong, this is not event-based vision. This is event-based serving frames. Here we are using events to enhance the image appearance, the image rendering, the image everything. This is events serving frames. And it's interesting, right? But if you go in this path, it's super great, but you're going in a path of rendering, of making images look better, or whatever you want to render to somebody. Very good. Great. But if I think you are interested in other options, this might not be the right sensor for you, right? So when you think event acquisition, I think what we all say here again and again, it's the world is changing. Is dominated by this. This is battery powered, so you have to reduce data. You have to put less current on wires and extract as many meaningful information. So, as Toby said it, and many times, it's stupid to burn energy to acquire something, then send it, then store it, and then throw it away. We all talked about that. So the solution is, I don't believe there is any generic solution. The DVS is not the absolute way of acquiring this type of event acquisition. And I honestly believe there is an infinite number of solutions. And this is motivated by one fact. If you take 5 minutes to see how many different eyes and vision systems there are out there, I don't think two can compare to each other. We can find similarities, but everybody adapts whatever he's doing to his environment. So there is no, it's not all about changes. There are many, many, many solutions, but you have to start somewhere, and that's good. Anyway, so I think what really matters is, whatever you're going to do in this field, what you care about is, can I get the dynamics of that scene and try to understand what's the nature of the data. That's it. If changes are what we could build in the 2000s with our 180 nanometer licenses. Probably there was better to do. So if you had to say, let me do a panorama, I think all of us can come up with something like this, like a spark sorting in a neuroscience lab. You can come up with two axes: integration time, how long does it take me to get an information, and power. So at one end, frames take time and they burn energy. At the lower end, you have events. They're almost continuous time. They burn very little. They burn, and you have something in between. Honestly, I didn't know power-wise if it was more or less. My belief is you can do it much less, but I put it somewhere in the middle, debatable. But what I want to tell you today is, although these look so different, somehow they are very, very similar, and at the same time, very different. So let me tell you why I'm saying this. I think when we do event-based and we really look at them very deeply, we are facing this type of things. We have on one hand structure, and we have on the other hand statistics. So don't look at the slide, look at me. I'm telling you a very funny story. Imagine you are looking at something, right? You have two main things you can do. You can say, yeah, I know that thing. Knowing that thing doesn't mean you understand how it works, right? I can see a gardener passing every day. Say, I know that guy. I don't know who he is. I don't know why he's passing there. But all I know is, I know that at 2 he passes by. I see him sometimes there. That's statistics. I know nothing of his life. I don't know if he's sick, if nothing. Statistics. So I know. On the other hand, I can understand. I can understand that person. Understanding meaning I will know his components. I will know how they connect to each other, how they evolve over time. So I know basically I can understand what makes him, what builds him, what's the connection between those pieces. And you see, this is fundamentally different. One is statistics, I know stuff. One is understanding, I deeply understand. If you have time to lose, go on internet, this is slightly different, and look for a video from Feynman that says, knowing versus understanding. And he has a very funny story. He says, you have two theories, theory A and theory B. Which one is better? This is not my words, this is all Feynman's word. So, in theory, A and B do the job, but one is better than the other. Anyone know which one is better? The better one is the one that you make a slight change and it can evolve into something bigger, whereas the other one can only do that. Now let us go back to event cameras. Event camera can produce frames and can do everything we do with frames with an event camera, right? But event camera can do much more. They have time, I will show you more than that. Whereas a frame can do lots of things, but can never be an event camera. Do you see the difference? One can evolve into something much bigger, while the other one is stuck there. So, a cat and difference, they all look different. But my daughter, who is 5, she saw one cat, and she knows it's a cat. Because they're all structurally identical. All cats roughly look the same, have the same behavior, have the same structure, but in appearance, they are so different. So if you want to recognize the cat, you have two options. You can try to get his statistics, and you're going to go to spend 30,000 hours to collect 10,000 millions of all the cats in the world to recognize one. That's knowing. And you have understanding. I know what the cat is, I know how he walks, I know his dynamics, therefore I can do much more from it. And so, vision so far, as you can see, uses frames. Therefore, everything we've done so far, people tried in the 70s to go to add velocity, but you can see images don't contain time, they don't measure things precisely. So, if you can summarize of what we do in an image, it's mainly statistics, appearance, it's knowing. Whereas, on the other hand, if you take an event camera, this is... Wait, let me stop this. I took this because I knew Toby was coming. This is caviar. This is probably the first time an event camera was connected to an FPGA, and the idea was to shuffle cards super fast. Everybody knows that? And recognize the tips and things. So I took that same baseline, that same data, and I'm going to sonify, this, because it had the feedback if I put the note. Yeah? You're good? So let us see, right? This is all dynamics. Okay? Do you hear structure? So what I did here is I did super pixels, and each time I got an event there, I put a note, a C, a D. Note, I sonified events and played them as a partition. As you can see here, although They are very different. They're also very, yeah. The space-time signature is completely different. So there is information. This is how event-based machine learning works. This is why it works, because there is structure. Now, if you want to learn this, you have many ways. You can smash it and go back to statistics. Good luck. Or you can play in this field here. And when you do that, what you are going to look for is how can I detect these structures, because that's what makes my information work. There's a very nice paper from 2015 that basically hinted about statistics versus understanding, where it's really nice. This paper shows why event-based has such a high dynamic, why the properties of temporal structure, of high temporal resolution, really bring something new to the table. So you see this A is moving around, like when you read it. And in space-time, here I'm only showing the orientation, the histogram of how many edges are oriented this way. So it's a histogram of orientation. And here it's, see the sum here? On the same statistics, I got the dynamics of how the number of pixels oriented by a bunch of time, a fraction of time, on an interval of time, evolve over time. And you can see an A, although looks very different statistically to a V in distribution, is completely different from a dynamic and a structure point of view, because structurally it is different. And this applies to everything. And the paper even goes to tell you what's the minimal, when can you become event-based, and when are you in frame-based mode? When is it statistics, and what's the temporal threshold that makes you go to the structure? Okay, that's the paper. It's done in an ad hoc way. I didn't develop the math myself, but it's really nice. So, to my knowledge, time surfaces do this structural learning. I'm going to tell you why. So imagine you have sets of events. Probably people didn't get that. And you have this last event arriving at time t. What you want to know is, how can I describe this structure? You see, it doesn't matter who speaks, it's when he speaks and where it is being spoken. So this idea we found was to create some decay over some tau. And when you look at the amount of value here over the curve, it gives you some vector that describes this structure, and that's what is called the time vector or time surface, so call it whatever it is. This is a structure, this is structural, this is not statistics, right? And so when you go to an event-based mode, it brings you something more about the structure. It's not that easy. It's a structure on many time scales, right? You're looking for dynamics. So when you have a time surface hierarchy, the first layers are very short, like in the brain. You want to get the features, what's happening. So your tau here, which is how far in the past am I going to look where my structures start, is what defines your integration time to define your structure. Not integration time, your observation time. How far should I keep something that is useful for me now, right? And so when you get those decays, you get the time surface. You get many of those, so you cluster. And then when you cluster, you get the best 4 clusters here. This is a toy example. And you see these clusters respond in a very unique manner. So this is not a static feature. This is describing an edge maybe moving this way or an edge moving that way. You see what I mean? It has space and time, both, and velocity, somehow normalized. And you can go deeper. Now, anything that comes from here will pass through the first filter and say, oh, that's feature number 1. Oh, and then it was followed by feature number 2. And you can scale it up again and again, which is really cool when you want to do an architecture, because you don't have to think much. But this time, you are not seeing how pixels are evolving. What's the structure of pixels? Now, the second layer is the structure of features. How do these features combine over time, over a larger time scale? Because now, you integrate more information, and then you get longer decays because you integrate more. You do the same thing, and now you have other time surfaces that describe the structure of space and time, but on larger time scale in the feature space. You see what I'm saying? And you can keep going, and you can do it on a month, on a year, on 20 years if you have data. You cluster again. See again, these features are now highly specialized as how the feature of the feature of the feature combine. And you can keep going until at some point your observation time is sufficiently long that you get some distribution. Hey, I've seen the feature 1 and then feature 2. You see what I mean? When the time scales become longer. And you can see they're all super different, right? And so, just show you an example. This is the Manchu, and he's moving his head. And you see here, it's color-coded by which time surface is responding. And the more you go deeper, you have many strategies. You can make your time larger, but also your space larger, depends. And what you see here is how it's detecting. I think this is the IBM database, but we just wanted to do a toy example. And the thing recognizes rolling and etc. So, although you've seen all this, what I wanted to say today is this is completely different from a normal machine learning. This is a different paradigm. That's why you shouldn't be using ConvNet, maybe to do the mapping between the timing and whatever you want. But fundamentally, we have access to something really unique. And reality is, as you can see, an image, a frame-based camera, and an event camera do the same job, but an event camera can do the job of a frame camera. The frame camera cannot. So this is present in nature. We know that the retina has two pathways. One is what we call magno and parvo. One is where, and the other is what. So what normally takes a bit more of time and it's normally a combination of fast and slow. This sounds familiar. So nature plays with this. This frames exist, or I don't think in the form we think of them, but something close to a gray level, I believe, exists and is used, and something like events is also used. So there is two mechanisms operating, statistic and structure. That's what makes us super strong, right? I can recognize it's a cat, but I say, I've never seen this cat before. You see? That's why you say the sentence. You can say this sentence, I think it's a cat, but I've never seen it before, because you're operating on structure and you're operating on statistics. All right? I see a human being, it's not my mother. You see? You have both. You need both. Because the world is described by its dynamics and its appearance. I'm almost done. Last. There's hope. There was this camera that this guy did a long time ago that I believed is the best. It's a very good camera in many ways. So it gave you all the time domain, the events, and the gray level all encoded in time. So now you have a very sparse and neat way to get gray levels, long, we don't care, statistics. And we get events. And it's all event-based, asynchronous, sparse, low power. And it's a pity this sensor is not built anymore. I think I saved as much as I could. And just to show you why this is so nice. So these are all data generate like 30 frames per second. This is 1 microsecond. It's not true, it's not really 1 microsecond, but you can see it's updated asynchronously. Every gray level there is asynchronously updated. And when you turn them, you see what everybody is talking about here. Frames, redundant, statistics, boring, slow, greedy, fine, but required, needed, important. On the other hand, you can have all this continuous gray levels, beautifully timed, and honestly not bad. There is a class of algorithm, unfortunately I think we are among the very few who wrote them, where we do computer vision event per event on gray levels, right? You can do it. It's not that different. But it's completely different from doing it with events and playing with time. Okay? But you can still rewrite those equations of image processing iteratively. So all I wanted to say today is images and events are they represent two different spaces that are required, are needed, and should not compete. They're both super important. One is low power and fast. One is more, and slow, because you need to integrate more cues. We have it's really rare that a field like us in this room are able to think, hey, we have a novel paradigm for machine learning. It's not statistics, it's structure. Okay? Thank you so much. That's all I want to say today.